So the problem that I did for you the other day with the concavity, and I actually redid that problem for the other section. I rewrote the whole thing out. There were two inflection points we missed in here. So it's up on YouTube and it's correctly done, and we do catch them. You just don't see them on decimals. They're really subtle. So those are caught and those are redone, so you can see that. And I'm going to do one more problem. This is related to a homework problem, and it gives you more insight into how these work. Boy, tired. I've cotton mouth. Just being tired, not from anything fun. No, there's seats here. As long as there's seats still open, just pile in. They're all nice. So on this problem, we have your favorite trig functions there. I know how people love trig functions. 1/2 minus cosine x from x equals 0 to 2 pi. And so here they constrain the interval because what does cosine do? Keeps going up and down forever, right? So if you do forever, you're going to get a bunch of critical points every time it peaks out. So they locked it down to an interval, and that interval is 0 to 2 pi. And the question is to graph it using derivatives. So you first cheat, you draw it on decimals, and you actually have 4 critical points. I hand drew in the last one. You have this one right here, it's flat. You have that one right there that's flat. This one looks like it's an inflection point. I think decimals drew that for me. And then we have this one over here that's flat. I think decimals just put this in for me. Let's see what happens. I'm only looking between 0 to 2 pi, so I only made the arrows between 0 and 2 pi. You have a similar problem to this that's been assigned to you for homework, very similar. It was constrained to 0 to 2 pi. That's not an accident. One period of this function is 0 to 2 pi. And you see that it's going up, flattening, going down, and that's it. It just goes up and down. So what does a slope chart look like? I can draw it. This is y prime. Now, I didn't write y prime here, but this is the y prime, how it looks. Well, it's going up and then down, positive and then negative. I dutifully put my y prime there. So this is what we call the slope chart. And we're back calculating in a way. Like I mentioned before, this is outdated. It's been long outdated. It's probably outdated in the late 1980s with Aquanet. It's gone. But still, we still have it in the textbooks. And it's outdated because you know how to graph things. No one in their right mind would use graphing with derivatives unless someone withdrew your calculator from you. So that's why it's outdated. So we're cheating a little bit and going back and getting the answers. That's what we're doing. Okay, the concavity, well, first it's concave up, then it's concave down, and then it's concave up again. And it seems to me that, you know, the important points for cosines are exactly those things you have to memorize on the unit circle. So my guess is that the concavity changes right around there and there. So where the concavity changes, that's what's called an inflection point. And right in between that point is that where the concavity goes from concave up to concave down, right here. Goes concave up, bucket that holds water, and all of a sudden that's a bucket that doesn't hold water. And I think it makes a switcheroo right there. And right over here, it looks like it makes a switcheroo again. So my guess is that that's pi over 2 and 3 pi over 2. Because aren't those important points on your unit circle? I told you I'm a weasel. So I think back to what was important on the unit circle and say, must be those two points. Pi over 2 and 3 pi over 2 is my guess. My hunches like this are usually right. It helps that I do this kind of stuff every day. My hunches get better and better. But when you have a good, it's a cooked problem. It's a textbook problem. So it's probably got a textbook answer. All right, so we get the y values for those things. You can even plug those numbers into your calculator. The y values are 1/2 and 1/2. And then we put those up on the concavity chart. Notice it has a y double prime there. It doesn't mean that I'm graphing y double prime. It means that I'm making the concavity. What are the signs of the second derivative? Well, whenever it's concave up, what's the sign of the second derivative? Positive. Whenever it's concave down, what's the sign? So that's what it looks like. It's positive before pi over 2. It's negative in between these two. and it's positive after. Now I could be wrong that this is pi over 2 and 3 pi over 2. I'll find out when I do the analytical stuff. It's just a really good guess. You with me? Everybody's with me?
So you plug in any number that's before pi over 2 into the.
Well, that's when we do the analytical stuff. That's when we plug in, actually have to do the plug-in. I'm just eyeballing and seeing the answers, right? So I'm looking at the graph and the split. This takes me about 30 seconds. Now I have the timer. I'm going to show it to you. So I time myself. It takes me about 30 seconds. I look at that graph and I can get both of these right away, right? So now it's like, if you had 30, that's as long as it takes to go into the back of your book and look at an answer key, which we're not even using this anymore, right? You have an e-book now, but that's so short. You look at it, it goes up, down, up, down. I got the slope chart. It goes concave up, down, and concave up. Dun, dun, dun. Where it switches, that's my only real guess. Okay, but my guess is based on the fact that this looks like, what number is close to 2 that's on the unit circle? Looks like pi over 2, right? 3.14 divided by 2 is like around 1.5, so it's probably around there. That's an important number in the unit circle. So I'm making some weasel kind of assumptions. You're going to find out that it's actually right. I'm so happy to see it's right.
This is the graph of the original function.
Huh?
This is the graph of the
Come up further, Bob.
That's the graph of the original function.
That's the graph of the original function. So I'm getting all the answers from doing those long 7 through 14 algebra steps. Okay, any other questions? So here's the long drawn out analytical steps. So now these are the steps that they used to ask students without actually having the original graph in front of them, right? So pretend you don't see the original graph. The object of the game is try to graph it. So it's silly, but we're gonna do it anyways. What you do is you first take the first derivative, and the derivative of 1/2 is 0. The derivative cosine is minus sine, but it still has a minus in front of it, and then we get sine x. So that's the first derivative. Then I set the first derivative equal to 0. And that happens at, between 0 to 2 pi, that happens at 0, pi, and 2 pi. And we can look at a unit circle just to remind you that. You still have your tattoo? No, you got rid of your tattoo. I told students that they should get it tattooed. Makes for interesting dinner conversation. Right, why get something useless tattooed on yourself? Get the unit circle with all the values on it tattooed permanently. You don't like that idea?
That wouldn't be cheating.
Your boyfriend wanted it. He's into the unit circle. Huh? What? Yeah, the sideways picture. So remember this thing from math is fun. There you go. They're telling you the y of the unit circle, and then I think they give you the whole thing right down there. They don't give you with radians. Maybe they give it to you later on. This one's with radians. Wow, that's nice. Someone hand drew it with better writing than me. Oh, it's a YouTube video. Do I have to go find a unit circle? You remember that the x-coordinate is the cosine and the y-coordinate is the sine. And but if you forget, it's not like I had that. I used to recreate that unit circle. In fact, in my pre-calc class, I showed them. I never memorized this thing. I'd recreate it. And if you have a calculator, you can kind of you can just remember, well, I think 0 is important. I think pi is important. I think pi over 2 is important. Because you start to remember which angles are important, and just plug it into your calculator, and then you'll get the y value. And I know what 1 over square root of 2 kind of was around, like 0.7. So I had kind of an idea, weaseling around and getting that unit circle. So that's how I know this. I know this not just from teaching, but from getting my weasel draft of the unit circle up and ready. SATs back then, you couldn't use calculators. So I had to weasel my way into getting that unit circle without the calculator. So I found a way. We're not going to do that here. We did that in pre-calc, but those are the important points. I label them on here, 0, pi, and 2 pi. I need values in between those points to find the sign of the derivative. I already know the answer. That's on my other slide. When you're writing on your page, you already can see the answer sitting in front of you. So I put pi over 2 and 3 pi over 2 in here. Crunch it on your calculator. Remember to put your calculator in radian modes. If you don't, if you have it in degrees, in physics class, they use degrees. Make sure that you switch it back to radians. I get that sine of pi over 2 is 1. That's the y value up there. And 3 pi over 2, which is on the 180 degrees, right? So it's 3/4 of the way around the unit circle. You get -1. And so it's negative there. So look at that. Just what we saw from the first slide with a little bit more effort, right? So it matches my answer. Make sense? Dean, does this make sense now? Because it was between 0 and pi. So cut pi in half, it's between 0 and pi. So I just need to find one number in between 0 and pi. Right. You could choose anything you want. You could choose pi is about 3.14. You could put 1 into your calculator. They'll give you some scary answer, but it'll be positive. And you could choose a pi and 2 pi, that's 3.14 and something around 6. I could choose 5, so I could plug that in. I just chose numbers because I actually do know these now by heart because I teach it. But before I had to recreate it here and there, and then I would just have my little cheat methods to recreate it, which I showed all my pre-calc students. This is really nice ways to get it. Okay, so don't forget you have to get the y values of these critical points. I'm going a little bit out of order from the steps. I tell you to get that first. Just don't forget to get that. The y values at x equals 0 is -1/2. X equals pi is 3/2. X equals 2 pi is -1/2. I just crunch it through. If you don't remember these values, just plug it on your calculator. Radian modes. So those are my CPs, my critical points. Exactly where I tagged them on the original graph, if you recall. That's exactly what I had to write in the 2 pi because I forgot to click it on decimals and I already screenshotted it. Okay, so everybody good with the first derivative stuff? It's same old, it's just trig function, that's all. That's the only difference here. Second derivative stuff, y prime and y double. We actually have y prime, we go to the second derivative now. The second derivative of sine is cosine, or the second derivative is cosine. And cosine is 0 at pi over 2 and 3 pi over 2 from unit circle. But you know what? If you forget the unit circle and you just can't call it to mind, just guess and test on your calculator until you find, is it 0, is it pi over 2? It's one of those, and it's either the pi values, the multiples of pi, or it's odd multiples of pi over 2. It's one or the other. So if you plug in pi over 2, you get a half. You plug in 3 pi over 2, you get a half. We already did this on the previous section, right? We already calculated these things. So the potential inflection points are these 2 points. Potential means it may not be. We found one in the other class, in the other section that we did. We didn't get an inflection point just because the derivative, second derivative was 0. Second derivative 0 just gives you the potential. You have to make that concavity chart. And so you choose points in between pi over 2 and 3 pi over 2 and plug them into the second derivative and check the sign, just like we did before. So I can tell you the soup that people make out of this. I know when someone's put the time into it early versus late. Not how much time, but when early versus late. What happens, the mistake they make when they go too late, they make a little stew out of the whole thing. They're plugging stuff into y prime when they should be plugging it into y double prime. They never plug things into y. They just stirred the whole thing up, put it in the oven, and handed it to me on the test. See it all the time. But for y double prime. So the information that you get, each one of these things gives you information to build that graph, supposedly assuming that you have no other way to graph but this, right? So the first thing that you get is a slope chart. It just gives you, like, where does it go up and down? That's what that gives you. The second thing tells you whether it's cupped, because if you have something that's going up or down, it could be going like this, right? You could have something going. This is always going up, right? So the derivative, the slope graph will tell you the slope graph for this and the slope graph for this is the same. It's up all the way through. It's up. Right? So you can't tell the difference between these two. The second derivative gives you the information of whether this guy or this guy. And that's going to be highly irritating when you watch this on the YouTube video because I just did on the board. But that's each piece gives you information like that. Okay, so plus, minus, plus, exactly the concavity chart I got from directly inspecting the original graph. So that I can erase potential and replace that with actual. When the definition of an inflection point is when the concavity changes. So at Georgia Tech and West Point, I would always see students that say, second derivative is equal to 0, therefore these are my inflection points, and they would just stop there. It's like they didn't have the follow through in tennis, you know, or the follow through in basketball. They just stopped. So that happens because they learned it as a procedure in an AP class, and they don't really know what that is. It's where the concavity changes, and the concavity changes at each one of these points. You can see it. Okay, so those are my CPs. This is the information that you gleaned in each one of those steps. That's all the important stuff. And yesterday, a student was asking me the order of how you graph. The first thing you do is you plot all the inflection points and the critical points. So I plotted those points, and then you use the slope chart. It goes up at the first critical point, and then it goes down between the second two. I think I drew that wrong, right? It's supposed to go all the way down back again. And the concavity changes right there. It's not a perfect graph. You're not going to get something that decimals true for you. But all that information is used to make the same graph that you got on decimals in the first place. That was the idea. Is it clear what you're supposed to do? So all that analytical work is just to get this, and that information. This is the information you use to build your graph. So as opposed to making a table and plotting x's and y's randomly, if you plotted x and y's randomly, what if you only had these 3 points as your x and y? Then it would look like a straight line. So you didn't have the full picture. So what you're really doing is you're finding what are the important points and only plotting those and the behavior between the points. That's what you're doing. And it's actually very clever. It's developed out of a need. Today we just don't need it. We need the other direction. We need to do the skill of looking at a graph and saying, what is it I'm looking at? Where's the maximum? Where is the minimum? Where is my mortality going to be the lowest? When is this person most likely? When do I have a predictor of when this person is diseased or not? So has anybody had the TB puff test before? If you work in a hospital, they make you have that. So you have the TB puff test. That's a diagnostic. They use calculus to figure out when that puff is a yes or versus no. It's a binary thing. I'm going to show you guys how to do that. I do it all the time. I build those diagnostics for different variables. If the placenta is not large enough, when does that not large enough tell me that it's a diseased placenta? So we use calculus to get that. Okay, any questions about this? I would like you guys to try one together in groups, and I'd like you to